For part one, we're going to talk about the central limit theorem. Now, if you recall, we have this distinction between descriptive and inferential statistics. So much of statistical analysis entails both, describing a set of data and also making inference about a population based on a random sample of data. So the first several parts of this course, really the first half, focused on descriptive statistics. The idea we want to describe the data we have at hand, usually a sample or less commonly a population if you conduct a census. But now we're sort of building up to inferential statistics, when we use a subset of a population, which we call a sample, to make claims about an entire population. So the idea is that when we talk about statistical inference, we're really concerned about understanding the quality of the estimates we have of the population parameters. Because keep in mind, we don't actually observe the population parameters, the mean in the population or the proportion of the population, because we don't have the population. We just have typically a random sample of that population. So a classic inferential question might be, how sure are we that the sample mean, x bar, is near the true population mean mu? So we don't observe that true population mean mu. So this is sort of the basic process of statistical inference. We have some population and we denote the full set of elements in that population with a capital N. So if you have, in the United States, we have about 320 million people. If that's your population, capital N is about 320 million people. And then the idea is, we talked about last week about taking a representative sample from this population. We typically use a simple random sampling procedure. And we gather a subset of the population. And we denote the number of elements in that subset, or that sample, lowercase n. Then the next step, based on this, using this idea that we have this simple random sample from a population, we want to calculate a sample statistic, such as the sample mean, or x bar. And we want to use that sample mean as a way of estimating or making a guess about that unobserved true population mean, mu, which we do not observe. And so that's that red arrow there. The idea is we want to go from the sample mean to the population mean. We want to say something about the population mean, even though we don't directly observe it. We just have the data at hand. So let's look at another example. The data set we're going to look at today is the Iowa census. It's actually sort of a census of several cities in Iowa in the early 20th century. So they collected data on people's age, their gender, their educational attainment, their location in several cities in Iowa. Now, this is a census, so we have the entire population, so we know the population parameters. In practice, we wouldn't actually know this, but it's useful for understanding this process by which we might be able to take a random sample and just use that random sample to say something about the population. So let's focus on taking random samples from the census, and then for this analysis, we're going to look at the average educational level. So let's look at this data set. We have these different residents of regions in Iowa. The data set here is truncated to 1,000 rows. In fact, the number of rows is much larger. And you can see we have several characteristics of residents. We have how old the resident is. We have a categorical variable for whether the resident is a female or male. We have this variable for educational level in years, and that's going to be the key variable for this analysis. We also have a variable for income, and then we also have a variable for location, where they are living in Iowa in the early 20th century. So let's look at education. Right? The great thing is, since we have this census, since the United States government actually collected information on everybody in these different regions, we actually know the level of the population mean for educational attainment in years. So in this data set, the average educational attainment among people living in Iowa is about 7 years, really 6.98 years. That's our population mean mu. But of course, conducting a census is very expensive and difficult, and so the idea is, with statistical inference, we want to take a random sample from a population and just use that sample to say something about the population, even though we actually don't observe it. So let's look at this idea of collecting a simple random sample. So suppose we didn't actually collect the census, so we didn't actually have all the information on people in Iowa, and we just had a list of the people living in these different regions. This is the sampling frame, right? So the idea is that what we're going to do is we're going to randomly sample people from this list. For now, we'll sample without replacement. And in this case, we've actually removed the names of the people, but each row is just a different person, right? So let's take a random sample. We're going to take a random sample of size 10 from the population, from these people living in Iowa, using our sampling frame. So we're just going to randomly select 10 rows from the sampling frame, and that'll be our random sample. And we're just going to measure these characteristics based on age, gender, education, and so on and so forth. And then the idea is we want to use a sample, or a random sample in general, to guess the average educational attainment of people living in Iowa in the early 20th century. So this is a random sample of size 10. And based on this random sample of 10 people living in Iowa, we find that the sample mean is 6 years. So based on the sample alone, we'd say, I think the average educational level in Iowa is, in the early 20th century, is about 6 years. I think that's about, that's our single best guess for the population mean. So the sample mean X bar, it's our single best guess without any additional information for our population mean mu. All right? So the next question is, we might say, how far off are we? Right? Well, the sample mean is 6 years. Right? Since we have the population, in this case, we know the actual population mean. The population mean is about 7 years. So we can see we're off by about a year. But that's, we might think that's pretty close. Right? Let's see what happens if we take another random sample of 10 people and calculate the sample mean again. So this is a different sample. It's a set of different 10 people. And in this particular random sample, we have the average educational level of 8.8 years. So that is our sample mean, right? This is just a simple random sample from the population. We might say, so you can see that there's some variation, right? Now the sample mean is higher. Before we had an average of, in the sample, of 6 years. Now we have an average of 8.8 years. So the sample means vary. The means of these different samples differ from one another just through the process of our simple random sampling procedure. But let's say, what if we were just to collect yet another sample? Well, for this third sample, it's a set of 10 people. We find that the sample mean is 6.55. So it's between these two values of 6 and 8.8, but they're varying. And this variation in terms of sample means, due to the process of taking a simple random sample from a population, we call that sampling variability. These point estimates are bouncing around. They're changing from sample to sample. So let's, for now, keep track of these different sample means using subscripts. So for this first sample, we had a mean of 6. So 6 years was our point estimate, our single best guess based on that sample for the population mean. For the next sample, we had 8.8 years as our point estimate. That's the sample mean for the second sample. And then for the third sample, we had a point estimate of 6.55 years. The variation, the differences between 8.8, and 6.55, those differences, that's called sampling variability. The variability in terms of our samples and our point estimates. So let's see what happens if we just were to create a dot plot of these three sample means, all right? So if we were to create a dot plot of these three sample means, we would find a distribution that looks something like this. This is in terms of taking 10 samples. So the average of our distribution of sample means is now about 6.5, right? What would happen if we were to take 30 samples? So what we're doing is we're taking 30 different samples from Iowa, and each time we're calculating the average number of years in terms of educational attainment. And you can see that there's some variation, right? Some sample means are above, some sample means are below. But the average of this distribution of sample means for Iowa is about 7.35. If we were to take 100 samples, so each of these dots, they're just different sample means, you can see that the average, the average of these different sample means is now 6.76 years. Right? These are just 100 sample means, 100 different simple random samples, there is variation. So that spread of this distribution, that represents the sampling variability. That variability is simply due to the fact that whenever you take a simple random sample from a population and you calculate some summary statistic, it's going to vary, just because through the process of random selection, the samples will differ. But on average, you can see that the sampling distribution, it's going to be centered close to that population mean, which we know, since we have the census data, we know it's about 6.98. Well, here's a distribution of sample means based on 1,000 samples. Okay, you can see the mean is about 6.92. As we collect more and more samples to set up a dot plot of sample means, we're converging closer and closer in terms of the center of the sampling distribution to the true population average, which again we know is 6.98. Here's a distribution of sample means based on 100,000 samples. Now this, of course, is these samples are based on width replacement because the population is not as large as the total number of observations here. But the key point is that this isn't just a sampling distribution. The average of this sampling distribution is 6.98, which is the same as that in the population. That's the same as mu. And then the spread here for this distribution reflects the sampling variability. So in sum, what we have is a sampling distribution. The distribution of sample means of the same size n, where lowercase n, it's the sample size. So the distribution of sample means of the same size n from the same population, we call this the sampling distribution. The sampling distribution of sample means is centered on the population mean mu. And then the thing to keep in mind is that although this mean from any particular sample, it's likely to be off. It's not going to always hit right on the population mean mu. On average, the sample mean x bar, it's our best guess for mu. And with that, we will explore several ways of actually looking at the sampling distribution and some of the properties of this process of creating dot plots of sample means and looking at the characteristics of the sampling distribution.